All right, we're back, and now we're going to look at another example. We're going to look at the planet Eris, a dwarf planet. And sadly for Pluto, Eris is the ninth most massive thing around the sun. So not only is Pluto not a planet, but it's not even the biggest dwarf planet. Eris, bigger than Pluto, our friend a dwarf planet, is the ninth most massive body orbiting the sun. It is more it's more massive than Pluto and 3 times farther away from the sun. Eris is estimated to have a radius of about 1,200 kilometers. Acceleration due to gravity on Eris differs from the value of g on Earth. So, I want you to imagine that an astronaut, what a boring thing to say there, when I could have said, Willem, stands on Eris and drops a rock from the height of 0.30 meters. The rock takes 0.87 seconds to reach the surface. Calculate the value of g on Eris. Oh. Well, remember, g is an acceleration. So pause this video if you get a second. See if you can figure it out. This is a nice, easy one. This goes right back to Unit 1, just calculating acceleration. But, you know, if you're not comfortable doing that, you can watch along right now. We'll do it together. But remember that when we talk about g, we're talking about an acceleration. So, let's take a look at how we would do that. Well, you remember your given, so let's take a look at what we know in this case. We know that he's dropping a rock from a height of 0.3 meters, so we can say the distance traveled is 0.30 meters. Okay, I like that. And we know that it takes 0.87 seconds. So we can think about that. So the time that's going to pass is 0.87 seconds. What else do we know? Well, I guess we know that, we're talking about an acceleration here, but we're, at first he's holding the rock. So I guess we could say the initial velocity must be equal to 0 meters per second, because he starts off holding the rock. We don't know the final velocity, but we do know the initial velocity. So what equation could we use for that? And if you go back to your dynamics equations, hopefully you're all yelling at me that what we want is delta D equals V delta T plus 1/2 AT squared. And I should put a delta there too. Be consistent. Not that I really care, but okay. Okay, I don't know why this is showing up so slowly right now. I am writing on that screen, but there we go. So delta D equals V1AT squared. And remember, since the initial velocity is equal to 0, we can just simplify that, and we can say that the distance is going to be equal to 1/2 the acceleration times delta t squared. And in this case, since we want to solve for acceleration, we can rearrange that, and I'll give you a second to rearrange that again, but we just would multiply both sides by 2 to get rid of that half, so we'd have 2 delta d, and then we'd divide by delta t squared to isolate the a, so we'd have 2 delta d over delta t squared. That's going to be our acceleration. And given that, we can actually plug our numbers in. So 2, the distance traveled is 0.30 meters. And the time it takes to travel that is 0.87 seconds. We need to remember to square that. And I'm going to switch to saying g on Eros here, because in the end that's what we're trying to find here, isn't it? We're finding g, and let's go into Desmos and see if we can do that. So we can say the g on Eros, the acceleration due to gravity on Eros is, let's make this so we have a fighting chance of seeing it. We said 2 times 0.30 meters divided 0.87 seconds. Then we had to remember to square that. And there we get it. So the acceleration due to gravity on Eros, quite a bit different from that on Earth. It is a mere 0.792 seconds. Meters per second squared, rather. 0.7. And how many sig figs do we have? Well, we have 2 sig figs. So we can say 0.79 meters per second squared. There we go. But we know we've got the version with 2 extra sig figs there for doing future calculations, so that's good. Okay. All right, from that, can we calculate the mass of the planet Eros? Planet Eros would be different. So now that we know the acceleration due to gravity, can we figure out its mass? Well, we know its radius is approximately 1,200 kilometers. So we know when Willem, our astronaut, is on the surface of Eris, right? So here's Eris, kind of a lumpy rock in space. I'm drawing it. I'm sure it will show up at some point. My connection's being flaky right now to this thing, which I find very frustrating. And our pal Willem is on its surface. $1,200 kilometers. Okay. I'm not sure which of these is behaving not nicely, but I actually think it's mine on this end. So I'm going to close it and reopen it. There we go. So we know the distance we're talking about here, radius of 1,200 kilometers. And then we know that we... And then what do we know about this? Well, we know that the mass of Willem, we don't know it exactly, and we could ask him, but we don't really need to ask him, because we're going to kind of do a 1 sig fig kind of thing here, and we know that he is going to be less than 100 kilograms. There's no way Willem weighs 100 kilograms. More than 50. So because he's between 50 and 100, then we can say he weighs 100 kilogram, and that puts us in 1 sig fig land. And the thing you're going to discover is that the number in question we're going to end up with is so big, so much bigger than, what we've got there, that we're good. So, calculating the mass of Eris should not be that difficult. But do we need to know his mass? I don't think we need to know his mass. I think we can do without it. We can do without, because we know that, what do we know? We know that acceleration due to gravity, well, we know that the force of gravity will just be the mass times acceleration due to gravity. This is one way to calculate it, right? And we'll say that's the mass of Willem. Yeah, it's going to cancel. So that's good. So I no longer need to insultingly imply that Willem is probably about, we'll say he's probably in the range of 75 kilograms. I don't know. So there we go. So now, let's see where we can go from there. So we know that the force of gravity should be equal to mass times that. But we also know that the force of gravity should be equal to the universal gravitational constant times the product of the two masses divided by the distance between them squared. Perfect. Well, our pal Euclid comes back again. Two things that are equal to the same thing are equal to each other. So, we can therefore say, whoa, that the mass of Willem times the gravitational acceleration Willem experiences should be equal to the gravitational constant times the mass of Willem times the mass of Eris divided by the distance between them squared. And the first thing you should note is that I can divide both sides by Willem's mass, and it goes away, which is not so bad. And now to solve for the mass of Eris is a relatively simple thing. We just have to multiply the r squared up to the other side, divide the g to the other, and we can say the mass of Eris must be equal to, g, little g, acceleration due to gravity on Eris is still on the top. R squared will be on the top, and the gravitational constant will be on the bottom. I think I've done that right. And so now, what do we know? Well, we need to know gravitational constant on Eris, but we do, so that's good. We have that right there. We need to know the distance between them, but we do. It's 1,200 kilometers. And we need the gravitational constant, but that's 6.67 times 10 to the negative 11. So we're good. This is going to work. So we can say the mass of Eris will be, I don't have that memorized, 0.7927. Meters per second squared times, I should slide this down a wee little bit. A little tight with what's above it. Times the distance between them squared, and we said that's 1,200 kilometers. We got to make sure we square that. And we're going to divide that by the gravitational constant, which is 6.67 times 10 to the negative 11 newtons experienced for every 1 kilogram system. 1 meter apart from one another. Okay. And let's do that. Mass of Eris. Oh, that's funny that I said eros there. That's the Greek word for love. One of the loves. The Greeks had, 5 words for love? Anyway, more than we do. Eros, agape, adonai. I'm running out, but there's more. There we go. And oh, 1,200 kilometers. Ooh, careful. Careful. Ooh, did we all note that? So, to make it meters, we just have to multiply it by 1,000. 1, 2, 3 more meters. Whew! Almost made a mistake there. Yeah, whoo, oh boy, that was scary. Sorry about that. Yeah, if that's 1,200 kilometers, that's it is 1.2 million meters. Okay, there we go. That makes more sense. Those units will actually cancel. And there we go. And so we know that the mass of Eris is going to be 1.7 times 10 to the 22 kilograms. Eris, a pretty heavy guy. And now that you know that, well, nothing to it. The C part is trivial. I could just leave it for you, but we'll do it together. Now that we know that, suppose that an astronaut stands on Eris and drops a rock from a height of 2.5 meters. How long will it take? Suppose that an astronaut. How boring. Suppose that Paul stands on Eris and drops a rock from a height of 2.5 meters. Oh my goodness. I hope not on to Willem, though with Eris's low gravity, dropping a rock from 2.5 meters is unlikely to really be very dangerous. Anyway, how long will it take the rock to reach the surface? Well, this is trivial. It's exactly what we did in A part. We could say the distance traveled is going to be equal to 1/2 times acceleration times delta t. And in this case, we want to isolate for delta t. So we can say delta t is equal to 2 delta d over a. And now we can just fill it in. 2 times 2.50 meters. And then the acceleration due to gravity we already defined, but I keep forgetting it, 0.7927. Meters per second squared. Oh, and that should be squared, so this whole thing should be square rooted. Yeah, just like that. And so if we do that, we can get our number. So let's pull up Desmos, and we can say time of drop is going to be the square root of 2 times 2.5 meters divided by 0.7927 meters per second squared. And we're going to get 2.511. So 2.51 seconds. Nice. All right. And we're in 2 sig fig land, so 2.5 seconds. There we go. That's that question done.